See, you know worst case analysis. In worst case, what happens? Suppose there is a, for example, I am just telling an example here. Say there is a for loop. Okay, I equal to say 1 to I less than equal to n I plus plus. Now there are so many statements S1, S2 like this. Okay, Sj.
Sir, one question, sir. Sir, one question, sir.
Tell me.
Sir, what will be our syllabus for the CA1, sir? Like till which part?
Last class, not this.
Okay, till last class. Okay, sir.
Yes.
Okay.
So for I equal to 1 to I less than n, I plus plus, there are some statements, these are executed. Now you know you can find out the time complexity of these. Say this is big O of 1, maybe. Say then that S2 may be another for loop if it is so, or suppose it S2 may be if condition. If some condition, then S2. Means if this condition is executed, then S2 will be executed. And S2 may take big O of n, suppose. Now in this way, all others are big O of 1. So now you see, if this is the case, what happens that if I have to find out the time complexity for this entire code, then what I will do, that this loop executes n times. And here I know that there are some big O of 1 statements, but one statement is that, for example, say S2 is like this, S2 is like this, means if if S2 is, if some condition C is satisfied, then statement S2 will be executed. And it takes big O of n time, the statement 2. So what we will take, that this is the n times, so big O of n. So to entire time complexity will be because the big S1, S2, S3 dot Sj, suppose there are say 10 statements. So Sn big O of n is the maximum, so big O of n will be for this statements, and as a whole, so it will be big O of n square, because n into big O of n means big O of n square. Now whatever you have done, it's okay, fine, no problem. That is also worst case analysis. Means you are determining the worst case running time of a data structure operation as a function of the input size n. Now suppose if this condition C fails most of the time, that means if it is not success most of the time, that means S2 will not be executed. Only few number of times this condition becomes true. Otherwise it is almost always false. So that means S2 is not executed. So that means I know that this big O of n, this statement, this one is costly, because it is, you see, big O of 1 is costly, this S2. Now if it is not executed most of the time, okay, so and then what will happen? I can ignore it, for example, although I should not ignore, but I am saying for making understand you, so that you think that if it is not present, then the time complexity will be big O of n, that it could be much less than big O of n square. Or suppose in some other way, if I say that okay, big O of n is fine, but it executes say 3 times out of n, where n is say 1000, then this statement is executed only 5 times. So is it good to take into account that big O of n will be this statement will be executed every time, and I should count it for entire operations, means for entire for loops?
No, sir.
So that means, is it not like that? Suppose you are in a mess hostel, say 100 students are there in a hostel, so 200 students are there. Now mess manager wants to calculate the total cost incurred for the mess that is run for a particular month. So what happens? So he is taking just the cost for one student, and he will multiply by 30. Now it may happen that he is selecting a students who takes a lot amount of food. You know, there are some few people are there, they really take a large amount of food, but most of them, others are taking not so large amount of food, and their consumption, food consumption are low. Okay, but please don't take it in other way. I'm just citing an example. Okay, so what happens if we multiply the cost, cost of that person who takes large amount of food by multiply by 200 students, will it be correct? Will it be correct that no?
No, sir. No, sir.
That means I have to average out something. That is called amortized analysis. So here also, we in amortized analysis, what we do? We determine the worst case running time of a sequence of n data structure operations. Okay. Example, starting from an empty stack. Suppose this is the empty stack. Okay. This stack is empty, and you have started from the empty stack, implemented with dynamic table. Any sequence of, you see, n push and pop operation takes how much time? Any sequence means, please remember that I can, I think I have discussed you that means like that stack permutation. That means you can push many times, then you can pop 3 times, 2 times, like that. So means there is not the case that first push then pop, then push pop. No, not like that. Any sequence of n push and pop operation, it will take how much time? You will see that it will take big O of n time in worst case. I can show you an example later. Okay. So anyway, there are some applications, amortized analysis, that you will see, that Fibonacci heap, garbage collection.
Sir, I have a question, sir.
Yeah.
I have a question, sir. Sir, when we are doing amortized analysis, sir, for example, you said that extremely costly, like for example, S2, which is an extremely costly operation, takes ON, which bumps up ON square if you are going purely worst case analysis. So in that case, in the amortized worst case analysis, do we completely ignore it or do we consider it for the 3 times?
If possible, always do that, because you have designed a nice algorithm, but what you are doing, your analysis is not good. Means you are overestimating. It may be n log n, but you are saying n square.
Okay, sir. So we're doing the optimal, realistically optimal.
Yes, your analysis should be also good. You don't think that I should be good coder, good programmer. Your analysis should also be good, because once you design a nice, efficient code, you should analyze it correctly. Okay, you will see that the example also in that heap sort also, heapify, massive, how much time it will take. There are so many applications, and this technique was that amortized time complexity was done by the Tarjan. I think it is 1985, this paper, amortized analysis. Okay, he is a Turing award recipient, Robert Tarjan. So anyway, so there are some methods. So see, binary example, binary counter. What is a binary counter? We have to increment the value from 0. Okay, so suppose we are representing a k-bit binary counters. So here, you know that mod 2 to the power k. So I'm not going to discuss that counter, means how it works, etc. Now here you know that counter means it counts. So all the numbers are generated 0, 1, 2, 3, like this. Okay. So here we are representing AJ by, what is AJ? AJ is used to represent the jth least significant bit of a counter. Okay. So now here you see the bit position A0, A1, A2, this column wise, A7. So this is the 0, you know, this is the 1, this is the 2, 3. Now how many, what will be the cost to implement this? What will be the cost to implement the binary counter? So here you see, I have to find out in the how many bits are flipped. Okay. So starting from the 0 counter, you see, a sequence of n increment operations flips n into k bits. N into k bits means, while I am assuming that at most k bits are flipped per increment, at most. Here you see, In this example, for example, you check here from this to this, you see these zeros because these bits are flipped 0 to 1. Clear? So you see that if I assume that at most k bits are flipped per increment, then it will take n into k bits. N into k bits. Now, if anybody thinks that I'll do like this, that what happens, you see, one interesting feature that you know already, still I'm saying that if suppose it is like that, this number is like this. This is a particular number, okay. Then what will be the next number? That 1 will be 0, 1 will be 0, this one third will be 0, 0, 0, 0. And this 0 will be 1. And then I will not change anything. Means whatever occurs at the left, I will not change it. Okay. So this, so that means you can, to implement this, what you will do, that you will scan from this side to this side. If it is 1, make it 0. If it is 1, make it 0. Okay. Until and unless you are reaching the first 0. First 0 from the right to left. First 0 is this one. So you will convert this first 0 to 1 and then you will stop. So that means you are accessing these k many bits. Fine. So if they, so therefore if there is n increment operation, means 0, 1, 2, 3, so it will be n k bits, n into k bits. Now you know if it is maximum number of means increment is n, suppose. Now tell me how many bits are required to represent a number n? How many bits are binary digits are required to represent
Log
a
n.
number? Log n, fine. So that means n into k value will be log n, k bits, na? At most k bits. So n into log n. These operations, entire operations will take n into k. That here it is, if it is k. So I am saying if k is n, sorry, if I increase the value to up to n, only up to n, means then k will be bounded by log n. So n into k means n log n. So it will take big O of n log n operation. If you do that, then you are correct, but your analysis is not good. It is much less than that. How can we do this? See, in this case, suppose here you check that 0, see, you see first bit 0, 1, 0, 1, first bit, it is represented like this. So here you see, I am writing here because this you check 0, 0. I am just taking 4 bits only. Okay. So here you see, this is this 0 becomes 1, 1 becomes 0, 0 becomes 1, like this. So first bit flips how much time? How many times? Bit 0 flips n times. So what is the cost? Actually you are changing the bits. That is the cost. That is the time complexity of the algorithm. So first bit is n times. Next bit you see, this is fixed. Check it. Then this becomes 1, 1. Change here. Then it becomes 0, 0. Okay. Then it becomes 1, 1. So this block size is 2. So that's why the bit 1 flips n by 2 times. Here it changes where? It changes only at this position. Check it. 1 to 0. Now next, third bit, you see you can form a group like this. It is not changed until this. Then it becomes like this. Then I have not written the other numbers, it will change. So here you see like this, so 4. So bit 2 will flips 4 times. So in this way you can count. So starting from 0 bit count, 0 counter, a sequence of n increment operation flips big O of n bits, not big O of n into k bits. How? Proof. You see the proof. Bit j flips n by 2 to the power j bits. Here you check bit 0, n by 2 to the power 0 means 1, means n by 1 means n. Bit 1 means n by 2. So I can write 2 to the power 1. Bit 2, so here I can write this is n by 2 square, this 2. Similarly, bit 3 will be n by 2 to the power cube. So bit j flips n by 2 to the power j times roll function. So total number of bits flipped is how much? I have to take the summation. So if you take the sum, then it will be this j equal to 0 to k minus 1. Clear? Now whatever be the value of k, but I know that k is less than infinite. So that is less than equal to j equal to 0 to infinity, 1 by 2 to the power j, and n is taken outside. Fine, because j only varies here. So what will be this value? This is n into 1 plus half plus 1 by 2 square, 1 by 2 cube up to infinity. So you know that is equal to n by 1 minus half. A the first term is 1 and 1 by a by 1 minus half infinity is sum. So that is equal to n by 2 and this is 2n. So this is 2n less than equal to 2n. So the total cost will be bounded by less than 2n. So this is big O of n bits, not big O of n. So if you say that the binary counter takes big O of n log n time, then you are correct, but your analysis is not good. Correct analysis will be big O of n. Why you will overestimate unnecessarily? So this is called amortized analysis. Now why it is amortized analysis? That I have shown you that in few cases here you see what happens. Here all the bits are changed. All the bits are changed. Okay. But there are operations where only few bits are changed. Only few. For example, you can see only here this bit is changed. Only one bit. And this is costly, so therefore. So this costly operation, this is the costly operation. So here you see 0, 1, only 1. Clear? But in this case, here you see 1 becomes 0, 1 becomes 0, 1 becomes 0, 0 becomes 1. So this is costly. So automatically you have to guess that whatever you are doing by taking the costly operation, that will be the worst case analysis, not amortized analysis. So if possible, try to do the amortized analysis. And that is this is called the aggregate method. Means you count all this. Okay, this is called aggregate method. Now another method is there. So that is called accounting method. Okay, accounting method, that is called accounting method, banker's method. Here DI, these are the formal notation. I will give you example that will be better for you to understand. So data structure after the ith operation is DI, and actual cost of an ith operation is taken as CI. This is the notation, and CI cap, that is the amortized cost of ith operation. Amortized. So here what is the case? The amount we charge for operation I. This charge can be larger or smaller than the actual cost. So when CI cap is greater than CI actual cost, then we store credits in data structure DI to pay for the future operation. And when CI prime is less than this, we consume credits in data structure DI. And initial data structure D node starts with 0 credits, always with 0 credits. This is the rules. And credit environment, Invariant means that doesn't change. So the total number of credits in the data structure should be always greater than or equal to 0. So your job is to choose suitable amortized cost so that this invariant holds good. So how can we do this? How can we do this? See.
Could you explain the the amortized and
I'm explaining through this.
okay, sir.
Accounting method, banking method. See, forget about the slide. You see, I'm drawing here that suppose this is 0, 0, 0, 0, 0. Then it becomes 0, 0, 0, 1. Okay. So every bit change, if you change the bit, it needs a cost. Means how much time it takes, that is cost. Fine. Now 0 becomes 1, and then in next stage you see this, then I am doing like this, then I am writing here. Okay. Now here you see what I am saying, that one credit pays for a bit flip. If you flip a bit, then one credit pays. Okay. Each one has one credit, each one bit has one credit, and each 0 has 0 credit. Initially all are 0, fine. Now I will assign cost. I will assign cost means how? If a bit changes from 0 to 1, we charge 2 credits. But if it flips from 1 to 0, then we charge 1 credit. 0 credit. Now you can ask me why you are telling this. Okay, that if a bit changes from 0 to 1, if it needs 2 credit, 2 rupees. 2 credit means 2 rupees. If you have problems, so you can think that rupees 2 is required. Okay, rupees 2 is required from 0 to 1. And 1 to 0, no rupees, means rupees 0. You may ask the same thing. If a bit is charged from 0 to 1 rupees 2, then why it should not be charged rupees 2 also from to change the bit from 1 to 0? It may be, yes, I agree with you. But why I am doing, I should be clever to analyze it. You see what happens, what I am saying. Okay, 0 to 1, rupees 2 is required. Now out of this rupees 2, actual cost means actually it will be rupees 1. Out of these rupees 2, actual cost will be rupees 1. Okay, and rupees 1 will be left. Okay, which will be used in future to change the bit from 1 to 0. What I am saying, that here you see rupees 0 to 1, it needs rupees 2. Now out of this, actual cost is actually rupees 1. Rupees 1 is required, and another rupees 1 that is left will be used in future to change that bit from 1 to 0. Because you see this 0 to 1, see here 0 to 1, this bit has been changed, but in future also this 1 will be changed to 0. So what you have done here, rupees 2 you have allocated to change this bit to this. Actually rupees 1 is required here, and when that will be changed to 0 in future, I will give another rupee 1 from this. That's why you see from 1 to 0 I have taken rupees 0. So here rupees 0 in this case. But Now you will ask me why? Why you are doing this? Here you see what happens in every increase of number sequentially. Only one zero is changed to one. You see, this zero is changed to one, single zero. Next, the next phase, 1 to 0 find, and 0 to 1, single zero. Next page, 0 to 1, this single. Okay, no other zero is changed to 1. Here you check, this 0 is changed to 1 only. So that means here in these steps, how many cost? How much cost? Here, rupees 2, 0 to 1. Next page, 1 to 0, rupees 0, 0 to 1, rupees 2. So total cost, rupees 2. Here, 0 to 1, rupees 2, 1, no other bit change, rupees 2. Here, 1 to 0, rupees 0, 1 to 0, rupees 0, 0 to 1, rupees 2. So you see, in every sequential operations, I need rupees 2, rupees 2, rupees 2. So if it is total n bits, means if you increase n bits, n times, so total cost will be 2 into n. Is it clear now?
Yes, sir. Yes, sir.
So that is called the binary, means accounting method. Binary. This is called binary counter. Okay. Mainly, you try to follow either this one or this one. Okay. This I am not showing the same. Another method is there. You may, if you are interested, you may check it. I am not describing it here. I will upload the slide if you are interested. But I do not use myself. I use that two methods. This is another method, potential method, that is physics methods. Now, as one good example, here you see. Okay, just a minute. Suppose there is a list, initial doubly linked list. So this is doubly linked list. The list is L. Okay, or say header is H if you say head. Now you have an array. You have an array. You have some numbers. The numbers are like this. Maybe sorry. Say like this. Now this is an array A. This is the list. What is the case? That it has been said that you will access the array. You will access the elements of the array. Elements of array sequentially. And what you will do? Okay, elements of array. Say if, say this is the numbers A1, A2, A3, A4. In this way, the numbers are this. Say AN. If AI is odd, insert it or append you whatever in the say this is the list. In list 8. That means initially it is okay, it is this. So what we will do? If it is odd, so you will do like this. So this will be the null, no problem. 0. Then it is 21. 21. Okay. So you will insert. Then it is 3. If it is odd, okay. Then you are accessing the 3. So it is odd, so you insert it just after it. The list will be like this. Okay. Then, but if it is, sorry, if AI is even, then delete all the preceding preceding numbers if the preceding numbers are if AI is even, then yeah, they are odd. So that what does it imply? That means then I am getting 6. Okay, so I will what I will do, if AI is even, then at first I will delete, I will append this, means the figure will be like this actually. Say 0, then 21. Okay, these are the pointers, you know, doubly linked list. And then 3. Then it was, I see, 6. Now it will check whether the previous element is odd or not. Odd, delete it. Delete means it will pointer, it will connect like this, you know. Then it is odd, delete. This pointer will point like this. So what after updating, the list will be like this. Okay. Now next 4 will be inserted. 4 will be inserted and this preceding element is 6, means even. So there will be no change. So it will be just 0. I am just drawing like this. That's 6, then 4. Okay. So if you continue this operation up to this, so what will be the total time complexity? So we can write a program. We can write a simple program to access all the elements of the array. So there should be a for loop. Fine. So how can I implement this thing? I can write a for loop to access all the array elements. And once I access an array element AI, then I will check. Means I will first append that into the list. I will append that number into the list. Any number into the list. Fine. And then I will check what is whether it is even or odd. If it is odd, you will do nothing. You just append into the list. If it is even, you append into the list and then check the previous element. If the previous element is odd, you delete it. If the previous element is odd, delete it, like that. So that means there should be another while loop. So if the number is even, then there should be a while loop to check whether the previous element is odd or even. And if it is odd, then delete it. If it is odd, delete it. Is it clear?
Sir. Yes, sir.
So what will be the time complexity? Tell me. I am not writing the code. In worst case, that I know that once I insert an even number, I may have to delete n by 2 numbers. Am I correct or not? Or say n by
Yes, sir.
I may have to delete. So that means that will take, while loop will take, in worst case, big O of n time? Yes or no?
Yes, sir. Yes, sir. Big O of n, sir.
And outer for loop?
Sir, another big O of
N.
n.
So
Yes, sir.
big O of n square. So whatever you are saying, that the total time complexity will be big O of n square. Clear? So, but here, whatever you are doing, that is worst case. So actually, what you can write this like this. For means I equal to, just you can write 1 to n. Okay, you append AI in the list. I'm not writing. Append AI in the list. After this, if AI is even or odd, if AI is odd, do nothing. Okay. Else, then there will be a while loop. While the preceding element of, just you can do. I'm not writing. Okay. Is even or like this. You can do. So in this way, you can write the code. And it will be big O of, you are saying n square. But this is worst case analysis. That is not amortized analysis. In amortized analysis, what you will do, you don't think like this. Means you don't look in this way. What you will do, you see, you tell me, this algorithm is doing what? What type of operation? Insertion and, tell me?
Insertion and deletion, sir.
Insertion and deletions. Operations are there. So if I can count total number of insertion and deletion, then we will be done. Fine. So total number of insertions and deletions. That is our question. If you can find out. Now you see, once an element is deleted, can it be inserted again in the array, in the list? Think and tell me. What you are doing? Here, you are deleting. If the previous element is odd, if AI is even, then you are checking what is the previous element. If the previous element is odd, you are deleting. Now, once that element is deleted, will it again come into the picture? Yes or no? If you are
Yes,
deleting
sir.
6, if you are deleting 6, can it come again into the picture 6?
No, sir. No, sir.
No. So that means if an element is deleted, it will never come into that. Now tell me, how many times you are inserting insertion? Total number of insertion? How many elements in the array? N. So you are accessing each element and you are appending or inserting that element into the list. So all the number of insertions is n. Is it correct?
Yes, sir. Yes, sir.
And number of deletion?
Sir, probably n by 2.
No. Number of deletion in
Sir, n.
C. No elements can be deleted. Yes or no? There may be the case that all elements are even. No
Yes,
elements
sir.
are deleted.
Best case. Best case, sir.
Best is 0. And in worst case, n minus 1.
Sir, n minus 1 elements are deleted.
Clear? So, total number of insertion and deletion varies from how much? N plus 0 to n plus n minus 1. That is equal to n to n to 2n minus 1. So it is linear.
Sir, O n.
Yes. So you see, Clear? This is the amortized analysis.
Yes, sir.
Here amortized means you are assuming that always the previous element will be deleted, and in worst case it takes big of n time. No, it is not so. And okay, so in this way, so what will be the amortized cost for single operation, means single insertion? If I insert, that will be constant time. If overall time complexity is big O of n and I am inserting n elements, so amortized and cost for insertion will be big O of n by n. For one insertion, I am asking. For one insertion, it will be big O of one constant time.
Yes. Yes, sir.
So this is the amortized cost. Is it not interesting?
Yes, sir. Sir, so
you-
is amortized the most efficient, like the most accurate
efficient.
one?
Yes. But it is not always very easy to find out. If possible, you must try. That will be very good. Okay. But you have to detect also where you are overestimating and how many times it can occur. Otherwise, it will be very difficult to find out. Okay, today I stop. And please let me know the date of exams. You fix it?
Yes, sir. Yes, sir. By today evening, we'll let you know, sir.
Okay, thank you.
Sir, also can you please share the recordings of the last week's classes?